what I'd like to talk to you guys today about with the nitrogen cycle is actually what are the controlling factors. Okay, so what's controlling these things, and to a certain extent, what is the consequence of this, of what's controlling these factors. So it's about nutrient cycling, the issue of essential for life and its availability, that thereof sort of controls this distribution. And this availability is controlled by these three things, these issues of the two different types of sources, the sinks and the pools, and I don't know why there's not sinks on that slide, and then the fluxes. Okay? Now these nutrients are, it's sort of each to its own because you need to have a very specific type of, the nutrient has to be in a very specific form for these organisms to use. Okay? Now, the largest sink of these nutrients are generally unavailable, because of this each to its own, the largest pool of these nutrients are generally unavailable to organisms. Okay? And so what you're looking at is a progression of different processes that produce a form that the organisms can in fact use. Now, there's a large amount of specialized organisms that in fact transform this unavailable pool into a usable form and thus make it available for all the other organisms. Okay? Much of this transformation of these nutrients, I mean, this is a soils course, so I want to talk about what the factors are in soils that are in fact controlling this. Okay? So much of this transformation of nutrients is in fact controlled by those soil characteristics, which are then controlling the organisms that are doing the transformations. Does that make sense? Yeah? Okay. So, back to these questions. These questions are basically building, okay, what are the pools, what are the sources and losses, and what are the fluxes? So we've basically answered these. Okay? Now I want to have an understanding of what's controlling these fluxes. Okay? And that brings us back to this slide. Okay? In the soil environment, what is actually controlling the nitrogen? All right? Now to answer that question, I want to basically pull things apart for a little bit. And I want to talk about what those sources are, what those sinks are, and what the specific fluxes are. That's what they are right here. Okay? Let's list them. Okay, things that are going into this system. There's primarily three types. One is anthropogenic, human source material. Okay, this could be intentional or unintentional. Atmospheric deposition is a big one. You know, those stacks are emitting stuff, and those stacks are blowing downwind and mixing with the water, and basically it's coming down. Okay, we also have inorganic fertilizer as well as organic fertilizer. And then we have all these waste products. We're fertilizing the world in essence. The sinks, where is the nitrogen? Well, the largest pool is the atmosphere. Then we have the biosphere, the biomass, and then finally we have the soil. The largest pool by far is this atmospheric pool. Okay, now these are the sources, there's the pools. What's controlling this flux between these pools? Basically, we're looking at a mobilization. And if we go back to the nitrogen cycle, that is that mineral versus a mineralization, a mobilization, mineralization. That's an ammonification through nitrification. That's the mineralization component. Okay? We have denitrification, taking it from the end of nitrification and turning it into N2 gas. Okay? Do we then have fixation, where it's taking that N2 gas, and it's biologically as well as abiotic, but it's basically taking that N2 gas and putting it in ammonium form. We then have plant uptake, taking that ammonium form, as well as potentially taking it in the nitrification form. And then finally, the nitrification form and the ammonia form, basically we potentially have losses through leaching as well as through volatilization. Okay, so those are the fluxes. These are the pools, these are the sources. Do we feel comfortable with that? We talked about this. And there's the cycle. Does the cycle make sense? The interesting thing about this, and we're going to be talking about 3 other nutrient cycles, and one of them I really shouldn't even be calling a cycle. The interesting thing about this nutrient cycle is that it is entirely mediated. It can be, I should say, it can be entirely mediated by biological organisms, primarily microorganisms. Every one of these steps that you see here, the fluxes are controlled by microorganisms. The microorganisms are then controlled by environmental factors, and this is a soil-driven system, except for the nitrogen fixation, which means it's soil conditions that are controlling these fluxes. So here are the fluxes again: immobilization, mineralization, nitrification, fixation, plant uptake, leaching, and volatilization. So what is going on in the soil that controls these fluxes? Now, you're going to see this question for each one of the 4 nutrients that we're going to be talking about. And it's going to be the same, basically the same thing every time. It's going to be temperature, moisture, climate, oxygen, and then the element itself, i.e., in this case, nitrogen, but more importantly, the form of that nitrogen. So let's start with temperature. This is a simple slide. You guys have seen this, I'm sure, many, many, many times. Okay? Biological activity versus some sort of gradient of temperature, degrees Celsius. Okay? There's a cold point and a hot point, and someplace in the middle you have maximum biological activity. Okay? When you start getting too hot, the system starts slowing down because you're starting to see denaturing of proteins and things like that. When the system gets too cold, the organisms can't operate because the biological activity at 0 is basically 0. That was not meant to be funny, but I don't think anybody thought it was funny, but it was funny to me. All right? Makes sense? Okay. Now, when we start thinking about moisture, I should actually put this at the back. This should be my last slide when I talk about moisture, but I like talking about this first because this really brings human activity into this sort of nitrogen cycle. Okay? What you see here is sort of a rice paddy or a wetland. Okay? And one can imagine in a wetland or rice paddies, we're basically looking at water as a dominant feature of that landscape. Okay? And let's talk about the nitrogen cycle, because rice, and as well as all these other plants, they need to have nitrogen in their plants. I mean, that's part of their essential nutrients as well. So let's use a rice paddy as an example for how we, in fact, control nitrogen cycling. Okay? So I've got a water level here. Okay, here's my rice plant. I have an aerobic zone of soil here. There's enough exchange between atmosphere getting oxygen into this water that it can get into this zone. Okay? If I get down below here, I'm in the anaerobic zone. Okay? Now, keep in mind that nitrogen cycle and what's controlling things. Now, if I am a rice farmer and I need to get nitrogen to my plants, what potentially should I do? Because I have an aerobic zone here, I could put in a surface applied urea. Okay? Now this urea is basically an ammonium form, in essence. Okay? And this material potentially will volatilize from the system because it's in a ammonium form, basically. Okay? And my nutrients potentially won't get to my plant. Potentially. Now, I also potentially can have that urea, the ammonium, basically go through nitrification. Now, this system is aerobic, so I can, in fact, have nitrification. Make sense? This nitrate is soluble, so I potentially will have downward diffusion or fusion movement out of the system, okay, through leaching, and I can have loss. Now, the interesting thing about denitrification is denitrification through nitrification is an anaerobic process. I will not have denitrification in an aerobic zone. Does that make sense? So, if I add my nitrate here, I'm not going to lose it as nitrate into gas. It's not going to be going that way because I have oxygen here. But the minute this nitrate gets down into the soil, which is anaerobic, this nitrate can now go through denitrification and turn into N2 gas, an unavailable form for plants, and it volatilizes and is lost from the system. Now, as a farmer, I know that nitrification is controlled by oxygen. Now, theoretically, if I put this ammonia here, I can lose it. But what happens if I take this ammonium and I put it into the anaerobic zone? If I put it into the anaerobic zone, I will not get nitrification. because it has to be in an oxygen presence. The microorganisms that mediate this, the Nitrosomonas and Nitrobacter, need to have oxygen. So if I put this ammonium in the anaerobic zone, I shortchange this, I stop this. And if I stop this, I'll never get this, so I won't get the leaching. Make sense? Now, the truth is this stuff can diffuse upward as ammonium. It's a gas. But it also can diffuse into my rooting zone. So as a rice farmer, if I had ammonium as my fertilizer, it makes sense for me to put that into the anaerobic zone because I'm going to maximize the uptake of my plants and reduce the amount of nitrification. Does that make sense? Now, as a farmer, does it make sense for me to put nitrate down here as a fertilizer? Certainly it's going to be soluble, it will move with the water. But also because the system is anaerobic, I'm going to be encouraging denitrification. And if I encourage denitrification, these are forms that the plant can't use, and it's a gas, so it will escape my system. So just by knowing the nitrogen cycle and what's controlling those fluxes, I have an idea about what type of fertilizer I should use and where I should put it. Good application of the nitrogen cycle. Questions? No? Cool? All right. Now let's step back a little bit and not be so sort of management based, but let's actually think about sort of the management that we do just by our daily lives. Okay? This is two different landscapes here. We're looking at an urban landscape or a developed landscape versus a forested or undeveloped landscape. And what we're basically looking at is we're looking at soil drainage classes. As you move through this profile from the uplands down towards the stream that's sitting here, you're going from well-drained soils up the uplands to somewhat poorly to very poorly drained. Okay, so we're basically looking at a topo sequence in this case of an upland system, of a developed upland system, a topo sequence from an upland system in the forested going down into the stream. Okay, the assumption is the water is moving this direction. Okay, now the size of the bars basically measure the height. The higher the bar, the more denitrification you have. Okay, what's denitrification? We're basically taking it from the nitrate to N2 gas. All right? What's controlling that? Go right back here. Denitrification is being controlled by this anaerobic system. You won't get it up here in the aerobic system. You only get it in the anaerobic system. Okay, so we look at the urban event versus the rural. In all cases, no matter where you are in the system, in all cases, denitrification is higher in these urban environments versus these non-urban environments. Now, why? The reality has to do with how we manage our water. It's not that there is potentially more nitrates here than here. I mean, we fertilize here. We don't necessarily fertilize forests, at least intentionally. Okay, yes, we have acid rain and all that. Okay, but in an urban environment, there might in fact be more nitrogen. But we're talking about denitrification, the rates of denitrification. What's controlling it?
Are you picturing agricultural areas as developed?
Well, agricultural areas could be developed, but I think we're also thinking about all the infrastructure that's associated with this. Okay, what happens when it rains in an urban environment? Things get wet. But where does the water go? As quickly as possible, they try to concentrate it and move it off. Okay? They put it into large water systems. And basically, they saturate the systems. The systems go anaerobic, right? In essence. Ish? Make sense? Okay? So if I'm trying to capture all of this and put it right into these zones, okay, I'm saturating down here. I'm flooding this zone while I'm trying to dry this zone out. Okay? This zone is wetter than that zone up here. But the whole system, the whole system is somewhat wetter, but it's not all concentrated. Okay, it's not all saturated. It's wet, but it's not saturated. Okay, so if I'm delivering more nutrients and I'm making the system more wet and anaerobic at the same time, not just wet, but wet and anaerobic because I'm concentrating it, what do you think is going to happen to my nitrification rates, denitrification rates? They go up. And so as a result, we see these quick responses of denitrification. Does that make sense? Now, this is not intentional management. Well, it is intentional management, but we're not intentionally managing nitrogen. We're intentionally managing water. And if the nitrate is moving in the water and we concentrate it, it goes anaerobic really quickly because we have these large storm sewers versus over here where we don't have that kind of concentration. The system's going to go anaerobic. We're delivering more nitrate. We're going to have higher levels of denitrification. Make sense? Another good example, and this has nothing to do with urban, this has to do with climate. Okay? What we look at here is this line right here represents amplitude. Okay? And this is the time of year. Okay? So the time of year, amplitude. Okay? And what you're looking at here, these dotted lines right here are rainfall. Okay? So a eutick moisture regime, pretty consistent rainfall. Yeah, there's going to be some stratification in there. You have big storm events and small storm events, but pretty much you have rainfall all through the entire year. Okay? In this system, we're looking at a eustic system where we have sort of a monsoonal type of event. In this case, it's a bimodal monsoon. Okay? We have a distinct dry period and we have distinct wet periods. Make sense? Okay. Now, what we look at, this dash line is nitrate N, excuse me, that is in the cropped soil. The solid line is the nitrate N that is in the bare soil. No crops. Okay? So let's take the top example. It's raining all the time. This is basically the growing season right here. We put our plants in. What happens to the nitrates that are in a cropped soil versus in an uncropped soil? The nitrate numbers. Well, in the crop soil, what happens to my nitrate numbers? They drop. Why? The plants are growing. They're sucking that nitrogen up, right? Does that make sense? Okay? But notice what happens in the bare soil. What happens to the nitrate N in the bare soil? Goes up. Why? There's nothing being removed from the system, but if there's nothing being removed, you probably should have a nice flat line. But we're seeing an increase in nitrate. What's happening? What's happening is nitrification. This might be the growing season for crops, but if I have a warmer temperature, I'm going to have more biological activity, which means I'm going to have more nitrification. Does that make sense? When we're talking about climate, what's this? Wintertime, summertime. Wintertime, summertime, right? And if microbial populations are driving this cycle, if the microbes are driving this cycle, it means this part of the cycle, when the temperature increases, that means that this cycle is going to increase, which means I'm going to have more of this. Does that make sense? Go.
Would it also just be because of greater nitrogen fixation too in those systems?
Well, if I got N fixation,
Then you have greater.
one would assume at this time of the year, nitrogen fixation, if this line represented biomass, I'd say yeah. But this line represents nitrate. And that's what we're seeing. Do the same thing for here. It's basically, in this case, we have an increase of rainfall. We have an increase in the crop land as well as an increase in the uncropped. What's going on there? Okay, in this case, this is going down. Okay, so we can make the explanation. Okay, we can understand the bare soil. Okay, I got more moisture. This is pretty much a uniform temperature area. Okay, but I have more moisture, so I'm having an increase in biological activity. Why am I also getting an increase in the crop soil? I mean, you would think, well, increased crop soil, I'd have increased nitrate removal, right?
Is that not what the plants are doing?
Well, the plants, I mean, it's this uniform temperature. You would think that these are both, the growing season has nothing to do with temperature. The growing season actually has more to do with water. So you'd almost have 2 growing seasons here.
Is it a little bit delayed after things start to dry? Like, does it not start until after?
Well, that could be, so you're really thinking most of the production is here. Most of the production is here. It's not actually at this peak. Because this is where you're getting germination. And actually that is in fact part of it. We're looking at a combination of wet soils. I mean, the soils are getting wet, and we're seeing a delayed growing season, which then drops this down. And you'll note that, look, this drop right here, see how the bare soil versus the drop that's in the crop soil. This is where you're seeing the crop response, taking that nitrate up. But I still have this point right here. The answer is right. What's going on, though? What's going on at this end versus this end? So, this part of the curve versus this part of the curve. This part of the curve, these 2 lines are basically together. This part of the curve, these 2 lines are separated. And the answer there is the crops. What's going on here?
So you said that in anaerobic zones that denitrification
Denitrification.
is taking place.
Right.
So how could it possibly be that it goes up when
Well, these systems are not necessarily saturated. I mean, we could use this curve, and I could change this to water. There has to be a certain amount of water to have biological activity. When it starts going down, we're starting to see anaerobic conditions. But here, it's not anaerobic. It just has a lot of water, but it's not so much that it's anaerobic. So there's another hand raised over there. And actually, this is the answer. But the question is, what type of biological activity? This is plants starting to suck those nitrates up. But who's producing those nitrates? Andrew, is that what you're going to say?
Well, yeah.
The microbial population responds like that. So it doesn't matter if I'm in the bare soil or in crop soil. The plants, on the other hand, are not necessarily responding yet. Okay, so I have this nice little peak, and then we see the drop. Does that make sense? You need to have the nitrate made. Something has to make it. Okay, and then it gets sucked up by the plants. And this is the microbial population that's making it. Go.
So is the peak, like that peak is caused by generally just the plants begin to produce at that point, or they begin to?
This is when the plants start taking it away. Okay, all you're seeing here is the plants aren't active enough to take all the nitrate away. Go.
would forested or grassland systems that aren't cultivated crops behave like the crop systems?
Grass systems probably would. Forested systems, I'm not so sure, because even in cold times, forested systems are actually taking up some nutrients. But I suspect you would still see this type of. The microbial population is going to respond a lot faster than the plants, and then when the plants start sucking it up, that's when you're going to start seeing that. Okay, cool beans. Questions? All right. Let's stay on controls. You've seen this slide before. What controls these fluxes? Well, the nitrogen controls. The nutrient itself controls the fluxes. And you've seen this one. This is ammonification, very much paired with nitrification. I can't have nitrification without the ammonium. All right? And then I start seeing denitrification because I can only get denitrification when I have that nitrate. Okay? Now, we're also looking at the pore volume issue here, but we're basically seeing a sequence of processes. Make sense? How about we take a look at denitrification? Okay, so we start with nitrate and we end with N2 gas. Okay, basically what you're looking at is a time scale here, a period of time, and a concentration. The higher it up it is, the higher the concentration. Okay, so we start this system at the end of nitrification, where I have lots of nitrate. Okay, the system goes anaerobic. What happens? Well, we start seeing the creation of N2O gas. Okay, and with the creation of N2O gas, the next sequence, the next step in this denitrification is N2 gas formation. And as we see this go down, we see the N2O gas start increasing, and then this is then converted into N2 gas, and we start seeing that increase. And the NO3 crashes. Sequence of events. It's the form of that nitrogen that controls the reaction. If I did not have this, I would not get this or this. If I didn't have this, I would not be getting that. Does that make sense to everybody? Go, Andrew.
So all that's anaerobic?
This is all anaerobic.
What basically controls whether N2, like nitrous oxide is produced or N2 gas is produced?
What controls whether this is produced or this is produced? Well, this controls this. Oh, it's a microbial population. It's a microbial mediated reaction. Okay? The microbial organisms are taking that and converting it into that. And then another group of microbes that are living in the same environment are taking this and converting it to that. And so this controls this controls that. Ultimately, this controls that. You have to have the nitrate to get the denitrification. Does that make sense to everybody? Questions? We cool? Good deal. All right, so those are the controls. What, in fact, are the consequences? And you're going to see this same thing again and again and again, depending upon what nutrient. We're going to be looking at plant growth. We're going to be looking at leaching and eutrophication. We're going to be looking at acidification and toxicity. This graph could be any nutrient, with a couple exceptions, potassium being one of them. Okay? We have a certain range of that nutrient, of its availability. So this is the plant response, okay, and this is the amount of nutrient. Okay, as I'm going that way, I'm looking at an increased amount of a nutrient. There's certainly a phase where the plants, they're deficit in that nutrient. And if they're deficit in that nutrient, they're not going to have optimum performance. Somewhere down the line, they're going to get the amount of nutrient they need to perform, and we're going to start seeing a sufficiency range or their optimum performance. Now, depending upon the type of nutrient, in some cases you'll reach a toxicity zone, and in some cases you'll get a range that we call the luxuriant range. Okay? In some cases that nutrient becomes a toxic element or a toxic factor in the soil, and in some cases it doesn't do anything. Okay? And it just sort of sits here and the plant doesn't perform any better than it did at this level. Okay? Potassium is a really good example of that. Okay? Nitrate, you get high levels of nitrate, high levels of ammonium, and you see this type of response. Okay? Now, another effect with nitrate and nitrogen in general is pH. If I start forcing my nitrates this way, lots of nitrates, what I'm going to see is I'm actually going to see a drop in pH. Okay? What you're looking at here is nitrogen fertilization application rates, and this is pH, 7, 6, 5, 4. As my nitrogen, I start applying my nitrogen more and more and more and more, I'm going to see a drop in my pH. Part of the consequence. Toxicity. And this is a concentration. This is actually ammonium that's in water. Okay? And this is a fish toxicity response. Okay? What we're looking at here is pH, and we're looking at temperatures. These numbers basically represent the concentration at which the water becomes toxic to the fish. Okay? So the lower the concentration, the more, I should say, whatever this number is, depending upon whatever its condition is in temperature and pH wise, that number at and below, or that number and above, is toxic to the fish. Okay, so if this is my ppm at pH of 7, this is parts per million ammonium, at 15 degrees Celsius and 7, if I have a ppm of 7.4 or greater, I'm going to have a toxic response in my fish. Does that make sense? You'll note that as the pH rises and as the temperature rises, that concentration number gets lower and lower and lower. When I start getting to the pH ranges of 8.4 and at a 25 degrees Celsius temperature, that's pretty warm, my toxicity of parts per million is 0.1. Now, this would be really low from a nutrient sense point for the plants if it was in a soil, but this is really high for the toxicity of plants, for the toxicity of fish. Now, compared to this, yes, this is a lower number than that, but that's a high toxicity at a very low number. Does that make sense? The consequence of that nutrient cycle.
Wait, so are you saying that a lower concentration is more toxic to a fish?
At higher temperatures and higher pHs, a lower parts per million in the water is just as toxic to fish as a higher concentration at a lower temperature and a lower pH.
Kind of one's like 19 degrees and 7.6 pH with...
If it's 19 degrees and 7.6, if the concentration is less than 1.5, they're fine.
Okay.
If it's greater than 1.5, they're dying. Does that make sense? Big sigh. Questions? We feel comfortable with the nitrogen cycle. We feel comfortable with the pools and the fluxes and the controls. Okay? Because as a farmer or as a waste manager or as a homeowner, these are the types of things that you should be thinking about when you're applying fertilizer or you're managing your waste. Okay? All right. Let's go to the sulfur cycle. Sulfur cycle is a lot easier. It's actually a lot simpler in many senses. Okay, when we talk about the sulfur cycle, it doesn't look that much different than the nitrogen cycle. And this is the whole cycle, and I'm going to give you a simpler slide to look at. Okay, but basically what you're doing is you're looking at a cycle. Okay, we'll start with a plant here. Okay, let's start with a plant here. Okay, the plant is taking up sulfur, okay, as a nutrient. It gets harvested in whatever form, and this example that we're looking at here is we're looking at a cow eating it. Okay, that cow and the residual material from this organic material basically gets back into the soil. Okay, now we can be adding this material as fertilizer, or we could be adding it as an indirect stuff coming from basically acid rain, or we could be putting it directly as fertilizer, in this case as an inorganic fertilizer versus an organic fertilizer. Okay, it gets into here. What happens to it? Well, it gets decomposed, and as it gets decomposed, it can potentially be converted, actually sort of oxidizes. It doesn't actually be decomposed. It can be decomposed into sulfates, or it can be broke down into sulfides. Okay, now the sulfates are the only form that the plants can take up. So this is how it comes back to the plant. But this sulfate, depending upon what's going on in the environment, a lot of different things can happen to it. The sulfates themselves can be absorbed onto the cation exchange sites. Okay? It also can be leached. Okay? It also can oxidize in simple chemical reactions that have nothing to do with organisms and basically turned into sulfur. Okay? It also can be used as an electron acceptor for respiration when systems go anaerobic. That conversion turns it into a sulfide. Okay? This sulfide, when it is exposed to oxygen, no biological mediation whatsoever, will oxidize back into a sulfate. Okay? Feel comfortable with this? This sulfide also can be reduced or oxidized into a sulfur. The sulfur can in turn be reduced into a sulfide. Now we can get sulfides as well as sulfates from soil minerals, large pools, and I'll show you a slide in a moment that talks about that. Okay? The sulfate can be leached. The sulfide can be volatilized. The sulfide can be volatilized and then potentially taken back and brought in as acid rain, depending on how it's processed. Okay? We feel comfortable with that? Let's actually take a look at the pools. Atmospheric pool is actually rather small compared to all the other pools. Okay? The lithosphere tends to be the largest. Most of the sulfur that's in our planet is in the rocks. Okay? The hydrosphere has some stuff that's basically run off the land. Okay, the pedosphere and the soil organisms, stuff like that, they also have a fairly large pool as well. Okay, in the soil organic matter, and in the land plants. The sources of sulfur tend to be fivefold for the pedosphere. Primarily, it's coming from soil organic matter, the decomposition of that material releasing the sulfur. Okay, we're also going to see sulfur coming from weathering of that rock material. Remember, that pool is rather large. We also have atmospheric deposition coming through acid rain. This is coming out of coal fire plants. We also have sulfur coming in in pesticides and in fertilizers. Okay, this is an anthropogenic source. Okay, some pesticides contain sulfur and it contributes to the soil, but its contribution to the soil is quite low. Fertilizers, once supplied, at one time supplied a lot of sulfur as an impurity, but today, because of the processing, sulfur, if they were giving you sulfur, they're going to make you pay for it. So they don't want to give it to you. Okay, so the purification processes are much better, and so sulfur is no longer really fertilizers are no longer really a source for sulfur unless you're intentionally buying the sulfur. Okay, and the last one is the irrigation water, and this depends upon where that water is or where you are. If the water is moving through the lithosphere, moving through rocks that have high sulfur content, and the rocks are weathering, that water is going to contain some of that sulfur. Okay, so it's really this groundwater, if you're getting it in your groundwater, that means the water is moving through rocks that have sulfur in it. Does that make sense? Okay, questions? Okay, 5 primary sources. Some examples, you've seen this slide before, in essence. I showed it with nitrate and I showed it with acid. Okay, basically we're looking at those coal fire plants and we're looking at downwind. Okay, the brighter the color, the orange the color, the higher the concentration. The darker the green, the less the concentration. All right, so those are the sources. What are the losses? Sulfur losses, obvious one is crop removal and uptake by the plants. So the plants take it up and then we remove the plant. Okay, when we harvest it, we're going to be taking the sulfur with us, or sulfur with the plant. Okay, we're also going to be losing sulfur through leaching. Sulfur is leachable just like nitrate. It just happens not to be as leachable. Okay, it will be moved out of that root zone by leaching. Okay, now just because it does not leach as rapidly as NO3 doesn't mean that it's not going to be lost from the system. So excessive rainfall or irrigation can remove that sulfate from the rooting zone down lower where the plants can't get it anymore. Okay, where are those pools when we start talking about the pedosphere? Okay, soil organic matter, and land plants. I have 3 different soils here. What you're looking at is the soil depth and then concentrations within each one and the profile. Okay, so you're looking at the larger the bar, the more the bar is over here, the higher the concentration. With mollisoils, high organic matter at the surfaces. Okay, high levels of organic sulfur at the surfaces. As you get into depth, you start seeing an increase in organic S and in inorganic sulfur. Okay, the predominant form of the sulfur in these mollisoils are in organic matter, and the predominant area that it's in are at the surfaces because that's where the organic matter is. Okay, another really good example here is this oxasoil. Okay, you guys remember the oxasoils? Okay, very small amount of organic matter dropping off, not anywhere near as much organic S as we see in these, but you see a dramatic increase in inorganic sulfur with depth. Okay, the other thing to look at here is sort of where these numbers are. Okay, then we also have the spodosoils. You guys remember? Question. Does the inorganic S increase because it's anaerobic? No, I think it has more to do with it's moving into the mineralogy, and well, actually with oxasoils it's probably not mineralogy. It has more to do with just the movement of that material down. It's in the sulfate form. It's not in organic matter. Okay, there isn't a lot of organic matter down there. Okay, go.
Is sulfate organic or inorganic?
Sulfate and sulfides, they're not inorganic or organic. It depends on where they are. If they're in an organism, we would consider it organic. Okay, and the organic source, then we'd bring the organic matter and watch it decompose, and then it would provide the fertilizer in that sense. It's not, I mean, the biomass component of it we consider it organic. And so this pool right here, the sulfur is associated with organic matter. This pool right here, the sulfur is not associated with organic matter. Does that make sense? So if you look at this scenario right here, because of the amount of biomass that's in this system versus this system that's actually in the soil, the sulfur in this case is not associated with, I mean, the vast pool of this is not associated with that organic matter, just because there isn't any organic matter. Does that make sense? Kind of-ish. Well, actually, let's take a look at this one then. Okay, this is the spotosols. Do you guys remember the spotosols? Those cool boreal forests, very bright E horizon, dark surfaces with BHs and BHSs down below. Okay, those are those reds and browns underneath a really bright albic horizon. Okay, well, if you think about how those soils are formed, they're formed through organic acids moving through the system, right? Well, those organic acids are stripping materials from above, the sulfur coming with it, and basically being captured in that organic acids basically sitting here. Okay? So what you're looking at here is the organic acids and the sulfur that's associated with those organic acids. Does that make sense? This is that BHS zone right in here. This is the E zone. This is the A zone, or an O potentially. So where is the sulfur associated with in these different soils? Mostly organic matter, mostly mineral material. Questions? Go, Lily.
Well, because like nitrogen, it can only be taken up by plants in the inorganic form, correct?
Nitrogen can only be taken up by plants with N fixation in the N2 form, but that's not the plants that are doing it, it's the rhizobia, or the ammonium form, NH4 plus, or the nitrate form, NO3 minus. Right? Those are, in essence, those are all inorganic forms. The plants cannot take them up as in an organic form. The microbial population has to break down that organic form so that the plants can take it up. Okay? So the plants in this case, the plants in this scenario, they can't take this sulfur up. But when this organic matter gets decomposed, they can take it up. The plants can only take it up in the sulfate form, SO4. That's their only option, the plants. Does that make sense?
Yeah, but it's SO4. I guess that was my question. Is SO4 inorganic or is it?
SO4 is inorganic. They have to take it up as an inorganic form. Yes. Now I understand your question. Cool. The fluxes themselves, we've already talked about most of these fluxes, but the flux that's really mediated by organisms is actually right in here. The rest of this, except for decomposition, the rest of the changes in the form have nothing to do with microbial populations. The microbial population is basically taking it from the sulfate form and turning it into the sulfide form. And they're doing it for a very specific reason. They're doing it because there's no oxygen present, and they're basically using the sulfate as an electron acceptor for respiration. Bang. Now, there are a couple of very interesting sort of environmental systems that this process is very important to. The first one is coal mining. Coal mining, basically, they're digging out coal. Well, where does coal come from? It comes from the ground. Yeah, it does come from the ground. But where was the coal originally formed? And don't say the ground. It was plant materials, and plant materials built up, okay, during the Carboniferous era, okay? They built up, and they were basically in anaerobic swamp systems, okay? A lot higher oxygen content of the atmosphere. Lots of greenhouse, basically a greenhouse operation, the planet, Okay? Lots and lots of plants dying in an anaerobic system. They go into wet systems. Okay? I've got lots of organic material in wet system. Well, what are the microbial population going to do? They're going to want to respire, and I've got all this food. So what they're going to do is they're going to use alternate electron acceptors. Iron being one, sulfate being another. So as a result, all of this organic matter is enriched with sulfides. Does that make sense? A couple million years later, we come along and we decide to start mining it. Well, we start mining it, we bring it up and we put it into the presence of oxygen. Now, that's okay as long as there isn't any water around. Because for biological activity to happen, it needs to have a certain temperature and a certain moisture. Okay? If I keep the coal and I keep it dry, nothing's going to happen biologically. So I burn it, okay? And we get these sulfides up into the atmosphere. Sulfides get up into the atmosphere, what's going to happen? Well, it's got oxygen and it has moisture. Forget about the microbial population. I'm going to have a simple chemical reaction that converts it this way. And if I convert it this way through oxidation, I'm going to basically make sulfuric acid. Make sense? Now, how about this scenario though? What happens to all the waste product from coal mining? Not all of it gets burned. In fact, mountaintop removal in Virginia and Maryland and West Virginia, a lot of that stuff basically gets dumped. Okay, and if it gets dumped in the presence of oxygen and it starts to rain, what's going to happen to that mine spoil? This is what's going to happen. And I'm going to make sulfuric acid, and I'm basically going to acidify all my streams. And I'm basically going to kill everything in my streams. Have you guys seen pictures of some streams coming out of some of these mountaintop mining removals? And they're like bright orange. And the pHs are really, really low. And in fact, remember me saying that there are some scenarios where we can actually make the pH lower than 1, 0? This is one of those scenarios with acid mine waste spoil. Okay, another scenario. Do you guys remember this? The hydrosphere? There's a good amount of sulfur in seawater. Okay? If you go into tidal wetlands and things like that, yes, you have the tide coming up, the tide coming down, coming up and down, lots of organic matter. But the systems go anaerobic at least once every 6 hours, right? If the system goes anaerobic, what's going to happen to that sulfur? What's going to happen to this? System goes anaerobic. The microorganisms that are doing the decomposition are going to find altered electron acceptors. They're going to drive it straight to sulfides. The reduced sulfur. Okay? What happens when we start dredging up the bottom of our canals to make sure that we have enough distance between the surface and the bottom so our boats can come through? We're going to dig this stuff up. And what do we do with it? Generally, we can't put it back out in the ocean. We have to bring it up onto the surface. We bring it up to the surface. It's in the presence of oxygen and water. Now, when it comes up, these soils have a pH in the 8s and 9s. Within a couple months, we're looking at pHs that are in the 3s and 4s. Okay? It's an interesting scenario if you think about it. And it's a very simple reaction. Let's skip this one. All right. So what controls these fluxes? Temperature, moisture, oxygen, and sulfur. In fact, I don't have to do a lot to talk about this. It's the same things that we saw before. Okay? I have an optimum amount, a deficient, and a toxic amount for plant response. Okay? We have all different sources of sulfur into the system. Okay? And if I start throwing sulfur up through stack emissions or through volcanic eruptions, that stuff is going to get into the air, at which point I'm going to get acid rain. Okay? Another toxic effect. Finally, if we think about how sulfur is available in the system, and we think about that sulfur cycle, The available soil sulfur that can be taken up by plants is this pool right here. Well, what affects that pool? Certainly things that are taking it up, actually right here, going up to plants. Those plants then die and come back or go into organic residual material, or that sulfur can bind with the organic material and become more available soil material. Okay? We also can have leaching, and certainly we can have erosion losses. We also can harvest. If we take that plant material, we harvest it, whatever we bring back will go into the system, but whatever we don't is lost. We can bring it in as fertilizer to make up for this loss. Some of it comes in with irrigation water, depending upon what the rock material the water's moving through is. We also have the rocks themselves that the soil is in. This stuff is weathering, bringing more sulfur into that soil pool. We have a number of losses here and gains through wet and dry deposition. This would be acid rain, for example, but we also could have volatilization of the H2S. That could be lost to the atmosphere. So in essence, if we think about that cycle and the available soil sulfur that can go into plants, we have to think about how we're controlling those fluxes from those various pools. And that brings us right back to that cycle. Okay? Interestingly enough, microbial mediation of this cycle is only here. Okay? Cool beans? All right, guys, be free. Have a great weekend.